If you make a mistake in data preprocessing, your entire machine learning experiment can collapse before it even begins. You can spend hours training a model only to realize the results are completely useless. Our objective is to take a raw, messy dataset, in this case the classic AutoMPG file detailing vehicle statistics, and transform it into a perfectly aligned matrix of numbers ready for a neural network. To do this, we rely on two primary Python libraries. We use Pandas to handle the heavy lifting of loading and manipulating the tabular data, and Seaborn to visualize it so we can spot hidden patterns. This process is essentially translation. We are converting human-collected, error-prone data into a strict mathematical structure that an algorithm can actually interpret. Executing the Pandas read CSV command maps the raw text file into an interactive table. The first column is miles per gallon. This is our target to predict. The remaining attributes, like cylinders, horsepower, and weight, are our features used to calculate that value. But raw data is rarely perfect. Running a quick check reveals that 6 specific rows are completely missing their horsepower entries. In Python, these register as nans, or not a number. We cannot train a model on a blank space. To prevent a crash, we drop those incomplete rows entirely. Our dataset shrinks slightly from 398 to 392 entries, but the remaining rows are fully intact. Leaving even a single null value in the dataset forces the algorithm to multiply weights by an undefined concept, causing the entire training matrix to fail. Now that the data is clean, we move to exploratory data analysis. This is where we map out exactly how these vehicle features influence one another. Using Seaborn, we generate a correlation heat map. Cells where two variables rise together show a positive correlation and glow blue. Cells where one variable rises while the other falls show a negative correlation and glow purple. If we look closely, we find something counterintuitive. High horsepower is negatively correlated with acceleration. In isolation, that implies a more powerful engine results in a slower car. We resolve this by looking at a confounding variable, weight. Horsepower and weight are heavily correlated. The cars with the biggest engines are also the heaviest, and that excess mass negates the raw engine power. We can view these distributions in a pair plot. Diagonal elements usually show standard histograms, stacking data into rigid bins. By switching to a kernel density estimate, the rigid blocks smooth into a continuous curve, showing the exact distribution density. Skipping visual analysis allows the model to draw false causal conclusions from correlated features. By napping the data out, you know exactly what information the algorithm is about to absorb. Before we feed this data into a model, we have to divide it. First, we randomize the dataset. This eliminates hidden sorting biases, like the cars being grouped chronologically, that would skew the learning process. Next, we execute the split. We dedicate 80% of the rows entirely to training. The remaining 20% is strictly quarantined for testing. From both of these subsets, we pop off the target variable, the miles per gallon. We separate it into its own set, so the model has a distinct answer key to measure itself against during practice. The test set must remain completely hidden during training. If the model sees the test data beforehand, it memorizes the answers rather than learning the patterns, making your final accuracy report completely useless. Our final step is standardization. Our features currently exist on drastically different scales. Cylinders are measured in single digits, while weights are in the thousands of pounds. To put them on a level playing field, we use a specific mathematical formula. First, we subtract the mean of the dataset, shifting the entire curve so it centers directly over 0. Then, we divide by the standard deviation. This squeezes the distribution so the variance is uniform across all features. This brings up a critical trap. When you standardize your quarantine test data, do you calculate a new mean from the test set itself, or do you use the mean from the training set? The answer is, you must strictly apply the training set statistics to the test set. In the real world, you evaluate new data points one at a time, meaning there is no test set mean to calculate. If you run unique statistics on your test data, you are leaking information about the future into the model's present training, ruining its real-world validity. To validate our pipeline, we check the new horsepower statistics. The standard deviation now reads precisely as 1.0, and the mean is at 10 to the negative 17th, a number so exponentially small it mathematically approaches absolute zero. We successfully loaded and cleaned the missing values, mapped the correlations to understand the mechanics, randomized and split the data, and standardized the scales. With our data fully processed and converted into a pristine matrix, we are ready to move into the next phase, actually training the neural network. Every step here is mandatory. A machine learning algorithm possesses no intuition. It relies entirely on the mathematical purity of the data you feed it.